In this video, I'm going to describe parallelism and how parallelism can be implemented on the hardware architecture side to get increased throughput capabilities and overall performance of a data warehouse. This is a continuation in a series of videos that build upon each other. So I would highly recommend that you, if you have not done so, watch the previous videos where I describe the data warehouse workload in great detail and give an overview of some of the more important hardware considerations. I also introduce query I/O statistics and cover how to gather those statistics either manually or through the new extended event framework provided by SQL starting in 2008 and greatly enhanced in 2012. I also cover how to set up and run SQL I/O tests, and I will also go back and readdress these things at the end of this session, but I highly recommend that you go back and review those concepts because they're vital in understanding parallelism. So parallelism is a critical aspect to data warehouse performance and scalability, and is something that is a great departure from thinking about architecting, let's say, an OLTP system, because an OLTP system fundamentally is about the opposite. It's about consolidation, namely the consolidation of your storage. And for OLTP systems, the architecture there is to have many disks, as many as possible, supporting one big group as a virtualized LUN. In other words, these disks, they function together as one, and the more disks that you add to it, the better IOPS you will have, the more IOPS you will have. While this is great for OLTP and maximizing your IOPS, for data warehouse workloads, this is actually the exact opposite of what you want to do. With a data warehouse workload, you actually want to parallelize your disk groups. So all your RAIDs, you want to have separate sets of RAIDs, each with a distribution or a portion of your database data on them. And then, so that way they can be queried in parallel and return their results in parallel, and thereby giving you the maximum throughput in terms of megabytes per second. So, and in the simple equation here, parallelism in the data warehouse world equals performance. So that's kind of, that's going to be the focus of this particular presentation. So, in other words, think about NUMA architecture. So NUMA architecture, I'm not going to go into all the details. You can use Google or your favorite search engine and read up on NUMA architecture. But the whole idea behind NUMA architecture is to parallelize what goes on between basically your main memory, your RAM, and your CPU. Because fundamentally your RAM is much slower than your CPU. Well, if you think of RAM, usually those are described in terms of megahertz, right? 1.6, 1.3 megahertz, whereas your CPUs are operating at much higher frequency. They're in the gigahertz range, and so to be able to make sure you're not burning a whole bunch of CPU cycles, parallelism is particularly through NUMA architecture, has been part of modern chip architecture for a number of years now. And so this same concept can be implemented on the hardware side, particularly the storage side for data warehouse storage. And so this concept is then implemented starting with the RAIDs, with the disk groups. Each separate RAID is then virtualized into a LUN and exposed to the operating system as a LUN. These LUNs can then be in a Windows server. They can be either separate drives or mounted volumes. Particularly, they're most likely going to be mounted volumes, because in this case, you're going to have several of these. You might run out of drive letters or save your drive letters for other things like mapped network drives and things like that. Mounted volume is just a virtual pointer that points back to the LUN from the operating system. You're also going to have to think about file groups. Your file groups, and particularly your database files, and I'll go over in detail how to set all this stuff up. But like I said, at the most basic level, your database files, you should have one database file on each of your LUNs or each of your RAID disk groups. That way, each database file will receive a portion of the overall database's data, and then it'll be queried independently of the other ones and in parallel, and SQL Server will be able to use, if set up correctly, all the RAID disk groups in parallel to satisfy data warehouse type queries. So, and in the next slide, I provide kind of two examples, and these are taken directly from a couple of examples directly from the Fast Track reference guides there that have great information, and I highly recommend that you download and really go through them in great detail. But here's what it looks like starting at kind of the RAID, the disk level. So this top example here, this is from the Dell Quick Start Data Warehouse, which is a fast track application that you can purchase, and it is a direct attached storage solution. So it is kind of more of a simpler design than the bottom one, and what it has for its database files is it has 9 LUNs, and both of these LUNs or disk groups are in a RAID 1 configuration. All right, so they have 2 disks for each LUN, and you got 9 of them. Then you got some LUNs for the logs, a couple hot swappable spares, and then on the front of, this is the rear of this 2U unit, and in the front you would have the 2 disks for RAID 1 for your operating system. So this is kind of a basic layout here, and even though it is direct attached storage, this is very, very effective for data warehouse workloads. As we'll see, I'll be able to demonstrate what this looks like, this exact architecture. There are other architectures also that if you read the Fast Track guides there, the reference documentation, there are more robust or more complicated architectures, and something similar to the one that is shown below. These are now RAID 10 disk groups, and so the RAID 10 disk groups now they're going to have 4 disks apiece. So they're at a RAID level 1 plus 0. So they're RAID level 1, and then it's duplicated. So you have 4 disks supporting each LUN. And here in this architecture, you have an enclosure would be on the left-hand side. Oops, the left-hand side there. This would be one enclosure, and it will have 1, 2, 3, 4 RAID groups, each with 4 disks. You'll have your logs, your hot swappables there, and then you're going to have 2 controllers controlling all this. And as you can tell from the controllers, that they're both capable of about a gig per second throughput. So that means that each one of these LUNs here is delivering about 500 megs of throughput, and that's pretty typical for a RAID 10 kind of configuration. You can get that kind of throughput. And then on the second enclosure, you have just the duplicate. And so both enclosures, when they're connected up to the fiber channel switch or whatever the switch technology is, then you're going to get a possible throughput capability here of about 4 gigabytes of throughput. So this is a kind of a larger system, and this is kind of an entry-level solution. This is the Quick Start Data Warehouse 1000 series. There's also a series that is more closer in architecture to this in terms of its throughput capabilities. That is the 2000. I'll be demonstrating what this looks like on a 1000 series, which is still a very good solution for most data warehouse environments. So hopefully that gives you an idea of what we will be looking at. Again, you want to keep in mind that we're parallelizing. So I'm starting at the disk, and I'm going to move all the way up into SQL Server. But even at the hardware level, things are going to be parallelized into several LUNs. And so on the next slide, when we move up into your file groups, so now I've taken the top example, the one from the Dell Quick Start, and so here's that same server and my same LUNs. So here's LUN 1 with or disk group 1 with 2 disks in that, and what that will have in terms of data is it will have a database file on it, right? all for the same database. So it's an Nancy, it's an NDF. So these are secondary data files. And so each one of these in this basic setup, now it'll get more complex in a little bit, but in this basic setup, each one of these LUNs has a database file on it. And so what happens when data is inserted from SQL Server, let's say in your nightly ETL load process, what happens is a page of data will go here, and then a page of data will go into your data 2, your second LUN, and then a page of data into your data 3 LUN and data 4. Now that's assuming that all these LUNs have roughly equal amounts of data in it. SQL Server does a thing called proportional fill, that if one starts filling up more than the others, it'll start filling up the other ones. But this is assuming that you're starting off with LUNs here that have relatively equal amounts of data in them. If that is true, then it just does kind of a round robin fill process. You know, page in your data file number 1, data file number 2, 3, 4, 5, and it gets to the end, and then if it has more pages to insert, it just goes back to the beginning and starts inserting in a round robin fashion. All the way through those database files. That is good because what that does is that distributes your data out amongst your disks, and so then when they're queried all at once. And so instead of being limited to just the throughput of one disk group, let's say 200 megabytes per second, you get out one disk group, you now get the aggregate throughput from all the disk groups, because they all contain the data that's being queried and they're all delivering that. So and again, this is a very important difference from something like a SAN or OLTP setup. An OLTP setup, you would want just to have one LUN that stretches across all these disks, where here we have multiple LUNs with the data sharded out or distributed out across the database files. So this is an example of starting the process of parallelizing from a hardware level, from a disk level, your disk groups, your RAIDs, and then your database files. Now our parallelism isn't finished yet, because we can parallelize this more. Because even though our data is sharded across or distributed across our multiple LUNs here with our database files, it is still not aligned to the number of processors we have. So the goal here is that we want to have our data parallelized all the way from the disk group to the database file, from the database file to the file groups, and directly onto the processors. So for example, in this configuration we might have, let's say, 8 processors, right? And so what we need to do is create a file group for each processor, and to have a portion of each one of these LUNs data on each one of those file groups. And so what that looks like is this. So this is the final configuration here. So, and we create a file group, like I indicated before, for each core that's going to be on our machine. And let's say for this purposes, and for this, because this quick start data warehouse has 8 cores, I'm going to use 8 as an example. So now what I have is one file group with a database file on each per LUN in my defined on my server, and this gives me better alignment to all the way through to the processing and then the processors. So literally each one of my 8 processors has access to a portion of the data on all LUNs. So here's my LUN, my disk group, and instead of having just one database file on there, I'm going to have 8. One for each processor, right? And then on my second LUN, I'm going to have, instead of one file group with one database file on it, I'm actually going to have 8 file groups, each with a database file, one for each processor. Okay? And so that way my processors are now parallelized, and my LUN groups are now parallelized, and all that parallelism it can be accounted for and optimized for. So this is kind of an advanced subject, and I've covered it real quickly. And if you need time or something like that, you can review, and feel free to ask me questions if you have any questions around any of this information. But what that looks like physically as an implementation, I can show you. So here, what I have displayed is a Dell Quick Start Data Warehouse 1000. And so here I am in my C drive. Now this has all that parallelism that I just described built into it. And so and as you can see, there aren't multiple drives here. This particular implementation has used those mounted volumes simply to conserve drive numbers and things like that, so you can also have mounted drives and other stuff on here if needed to be. So the way to see these different LUNs is to go into the FT folder, and the PRI, that just happens to be where these links, these are essentially just virtual links out to for the operating system to use, but also you can use it when you're using the file system through the UI to go out and access all these LUNs. So these are my LUNs, essentially LUN 1, which is these are all RAID 1s, so these represent 2 disks. So here's 2 disks in the first one, and the second one, third one, fourth one, etc. And I actually have 9 in this case. And if I drill in, let's say I drill into the first LUN, what I get is, now this situation is a little bit more complex than what I presented, and I'll go in a little bit more detail maybe later on in subsequent videos, but what I'm right now doing is presenting kind of the basics. And so for the purposes of this video, what I want you to concentrate on are the first 8 database files. So each one of these database files comes from a separate file group, right? So I'm in LUN 1 data. This is V data 1 is the name of it, and it has 8 database files, each from a separate file group, so that SQL Server can affinitize all the way from the 8 processors down to individual file groups like that. That means that when you're creating tables in SQL Server, you need to be cognizant of this. It's not a very simple exercise, because now you have multiple file groups to contend with, and this particularly becomes very important for when you're partitioning fact tables. And this will make your partitioning of fact tables a little bit more complex, but if you understand what's going on behind the scenes, it isn't too bad. But all this is done, although it seems like, and it is additional complexity, this is done to achieve the maximum performance through the use of that parallelism. Okay, and so the other LUNs here, I think one of them is for a volatile and a stage kind of file group, and then of course there's temp file group as well. So what I want to point out is, and this is this goes back to my previous videos when I had a chart of SQL.io and the results of SQL.io against various architectures. What I want to point out, and so this is a follow-up on SQL.io, is that I have a SQL.io set of executions here, and actually some results that are still here as well. What I want to point out is that when I run SQL.io, and I have my test file on this LUN, this group of disks, I'm only testing this one group of disks, so these 2 disks. There are other disks that will contain the database's data as well, and so if I wanted to get an accurate idea of how all these disks perform in parallel, I have to put an instance of SQL.io on each one of the LUNs and execute it in parallel, and then take my results So my overall performance is not 224 megabytes for the overall Quick Start data warehouse. It is 224 megabytes plus the performance of all the other disks, all the other LUNs when they were executed in parallel. So I have to aggregate all those together to get the final number. And so that's what I did with that chart that I displayed previously. So that's a very important thing. So just to recap, what I do is first I execute SQL in most cases when I don't know the architect, and you have to have a very good understanding of the architecture, hardware architecture. What I do is try to find the optimal performance peak for an individual set of disks, and then if the database is spread out against multiple disks, then I use those same parameter values and execute SQL.io, multiple instances of SQL.io, one on each disk group in parallel, so I get then an understanding of how all these disks perform in parallel, because that's important because the database data will be spread out across all those disks. So that is SQL.io. And going back here, if I go back to my second, you can see that my second one is a mirror copy here. My first 8 file groups with one database file each is on there, and of course I have a separate instance of SQL.io on here as well because I did do that. I did execute all these SQL.ios in parallel to get an understanding of how this particular system functions when all the disks are being used in parallel, because that's what happens at query execution time. So, and the rest of those disks those LUNs 1 through 8 are set up virtually identically. So now that I described the disk groups, the LUNs, the file groups, and the database files, how they should be properly architected to get maximum parallelism, we can see it in action on this Quick Start data warehouse. So on this Quick Start data warehouse, what I have a sample database, and it's just an expansion of the EventuWorks data as well, and I have a table which already has a column store index on it, and it's got about 100 million rows of data on it. Now what I'm going to do is I'm going to simulate, in order to test the throughput, because it has a column store index, I want to ignore the column store index. With the column store index, I only get about 800 reads out of it, and that's not enough data to really see what this is capable of in terms of throughput, right? Because the column stores are so efficient, they don't really test the throughput capabilities in one query of a table this size properly. So what I'm going to do, and you'd never want to do this in production, but just for the testing purposes, what I'm going to do is I'm going to add in this option to ignore the column store index. Alright, you can do this explicitly. I do not recommend doing this in production, but I'm doing it for the purposes of really testing the throughput capabilities of this system and make sure I'm getting good throughput there. And of course, like my other ones, I'm going to drop my buffers, make sure I'm pulling directly from disk, and turn on my I/O, and time statistics will be important here. So, and if I execute that, now keep in mind, look at my query. In terms of its logic, it's very simple because I want to have as little CPU interference as possible. I just want to be testing how efficient or how performance of throughput is handled in this system, and so I just have a simple count on here. Now recognize, for those of you who like using the select count a lot, is that I'm literally, even with a select count, I'm literally pulling across all those data pages. And so if you want to know how to kill a system with a very large query, you know, a select count can do that for you very easily if you don't know what you're doing. So now here are the results. I've already gone ahead and copied and pasted them And these runtimes might vary slightly in terms of several milliseconds from what I just executed, but logical reads are going to be the same. So here I have about 1.4 million logical reads. And that works out to about 11 gigabytes of data. So 11 gigabytes of data was returned in this query in about 9 seconds. Now, my CPU time, I'm just going to go off the one I have up here. My CPU time is, now this is in milliseconds, so this is about 39 milliseconds. So why is it 39 milliseconds when my total query time is only about 9 seconds or 10 seconds? Well, the reason for this, how can my query time be longer than my total query execution time? Well, that's because of what I just explained, this parallelism. Because of those file groups and those database files and those LUNs, everything is parallelized all the way up to the CPU cores. And so this particular machine has 8 CPUs. Sorry, 8 cores. So that means that this total query CPU time represents the aggregate total of all 8 of those CPUs. And so what I need to do is divide by 8, and that will give me roughly, and this is just basically an estimate, because sometimes they're not parallelized exactly perfectly equally, so depending on the query and the logic and those kind of things. But for these purposes, because it was very simple, I'm just going to divide by 8, and so that gives me an average of about 5 seconds or 4.9 seconds per CPU for this particular query. So of this about 10 seconds, 9 seconds for the total time, about 5 of that was dedicated towards CPU, just aggregating things. So if I subtract that from my total elapsed time, I'm left with about 3.3 seconds, or 3.4 seconds. So my total elapsed time minus my individual CPU time, which I had to take into account that the parallelism was going on, gives me 3.3 seconds. And so of this total query execution time, about 3.4, 3.3 seconds was dedicated just to waiting on disk. And because that was 11 gigabytes of data divided by 3.4 yields a total throughput for this particular query of about 3.25 gigabytes per second. So, and if you recall from which is spectacular performance, by the way, if you recall from a previous presentation that I made about the comparison of architectures here, my SQL I/O results were only about 2 gigabytes. So why can I get 3 gigabytes in that very simple query, whereas in my SQL I/O measurement of Quick Start Data Warehouse, I get 2 gigabytes? Well, the answer is a great lead up to the next section that I have. And so fundamentally, the reason for this is that SQL I/O, when it creates that test file, remember, and I described in previous videos the importance of understanding that test file. When it creates that test file, it just writes and reads data. Now, the way it creates that file by writing the data the way it does, it doesn't do it as well as SQL Server database engine does, meaning the data is fragmented, and fragmentation is introduced. And whenever fragmentation is introduced, these are literally, in terms, now these disks in this Quick Start Data Warehouse are not solid state drives, they are spinning media. And so if you think about the spinning media and tracks and head movement, with more fragmentation introduces more head movement and will slow down your throughput. Now this table that I created is kind of the ideal situation. It is created once and just used for demonstration purposes. And so the data represented by this table has very little to no fragmentation in it. In real life production scenarios, you're going to have fragmentation. Any type of DML operation, insert, update, or delete, will always introduce some type of fragmentation in your table, and so you're always managing that. So I'm able to actually exceed my throughput capabilities, and because I'm not bound in terms of my I/O components, I can actually exceed that 2 GB limit, because one, SQL Server uses things like extents and extent allocation that I have specially configured to make this data very unfragmented, very low levels of fragmentation. That means less disk head movement and translates into greater throughput. And I'll go into more detail later. So your question might be, why do you use SQL I/O if it has inherently more fragmentation in it, and why don't you just use query statistics like this? Well, for one thing, this is an unrealistic scenario because this is a pristine table, and because even though SQL I/O does introduce a little bit of fragmentation, that's actually more realistic or more comparable to live production workloads and mixed query as environments as well. So, and SQL I/O is the standard for all the fast track reference architectures, and so that's why I stick with this. It's a more realistic standard, which is what I just showed you is kind of the most ideal situation possible in this kind of performance. But it's still a great performance. Performs very well in data warehouse situations. So that is all I had for this video. And then the subsequent videos, I'm going to go over more in detail fragmentation and exactly how SQL Server can be configured to really reduce this fragmentation, because as you saw from my example, reducing fragmentation can have a dramatic impact on the total performance of your data warehouse. So being able to manage that becomes absolutely critical. Thank you for your time.